Hello and welcome to another day of Advent of Code. In this one, we're going to be dealing with a bit twiddling puzzle. I thought this one was pretty easy, but then again, I'm pretty comfortable with bit twiddling, but I'll give a little refresher on that before we start. Anyway, let's jump into it. Okay, so the puzzle for today, let me open up. So unfortunately, the input and the actual stuff is interspersed, so we're not going to do a separate parsing today. We're going to do the parsing as part of the puzzles, and I actually have a different parsing for either part. But anyway, the input looks like this. You're going to have a series of bit masks and assignments, and they might be interspersed throughout each other. And these bit masks have different rules. So for part one, the x's are all ignored. So if you see x's, they're all ignored. And the ones and zeros assign those bits. So it's kind of annoying that these are in base 2, but this is in base 10. And that's another thing that tripped me up a little bit, especially because this looks like it could be a base 2 number. But anyway, these are in base 10, so not base 2. And the mask, in this case, for part 1, overwrites the ones and zeros. So it only takes the bits where the x's are. And the mask is applied to the values, not to the memory addresses. And at the end, we're supposed to say what the sum of all the memory is. This is actually the same for part 2. And so that's part 1. For part 2, zeros are ignored. So you would ignore all of these. And the ones assign those bits. So the ones matter. And then the x's are cycled through. So there will be every combination of each of these two x's, like either 1 or 0 for both of them. And these are applied to the memory addresses, not to the values. And because these are cycled through, that means that the memory addresses are going to have a bunch of different values. And yeah, and so again, the end is the sum of all memory. Now I want to show you a few operations that's going to make this problem maybe a little bit easier, or at least how I approached it. And those are the bitwise operators. This is just Wikipedia, so you could look this up yourself. But we're mostly concerned with bitwise and, which with bitwise and, if both are ones, that is the only time that it becomes a 1. So you can kind of think of this as like everything is ones. The other thing that this can also do is if you and with a 0, it's always going to be 0. And then there's bitwise or, which is either of them is a 1, we'll end up with a 1 at the end. So if we look at kind of the first problem where like zeros and ones set those bits, the way that I'm thinking here is that, you know, the zeros are going to and the ones are going to or, because we need to or to get ones and we need to and to get zeros. So we're gonna have two different bit masks based on this. Part 2, it's a lot more complicated. We know that we're going to or to get the ones. We're going to ignore the zeros, so we don't really care so much about that. But when we cycle through, we might be doing anding or oring based on whether it's a 1 or a 0, similar to how part 1 works. I didn't actually reuse any of my part 1 code in part 2 other than my parsing bits, but you know, we'll see how that goes. The other operations that I'm going to be using is we're going to use bin a lot to visualize stuff. So say we have this binary number, you can use bin in Python to kind of visualize this. This helps a lot with looking at stuff. Unfortunately, it doesn't work well for negative numbers, where it helpfully says that this is negative 1, 0, 0, 0. But for a negative number, I think it's just the bits are flipped. So you can imagine this is the opposite of those bits. Actually, we can just do unary not, which is a bit flip. And see that it is 0, 1, 1, 1. So yeah, it's just a bit flip there. So that's perhaps easier to see. The other thing that I'm going to use is if we have a bit and we left shift it. So this is left shift, and then we visualize it in binary. So this shifted this bit over by 6. So 1. Well, let's do it. Let's do a smaller one. So it was here. And it got shifted 1, 2, 3 places over. There's also right shift, which, you know, if you left shift and then right shift, you'll get back to the original number. We'll be using this in our solution as well. So those are most of the bitwise operations that we need to worry about. Let's actually get to implementing this. So for part 1, I noticed that these, you know, you can probably parse these with split. I parsed them with regular expressions because I felt that was easiest. I felt that this one was easy enough to do with split. This one was a little bit more complicated, but I don't know. I made a regex. So re reg, let's see, pattern equals re.compile. We start with mem. We're gonna make this a raw string. We have an ignored bracket. Then we have digits. Then we have another ignored bracket. We have space equals space. And then we have digits. And then we end our regex. So that's a pattern that'll match this line. We'll double check that when we actually go through this. And for this one, I think we're just going to split. Now note here, we kind of have a little bit of a state machine here. So parsing in and out, or parsing this up front didn't actually really make this problem any easier to understand, in my opinion. Okay, so let's see, how do we solve this? So we're gonna have two different masks. Oh, we also need to set our memory. So our memory here is going to be a default dict. Let's see, memory equals collections, default dict, int. And I'm using this so that when I assign into it, I don't care whether the slots already exist or not. I guess technically I could have just used a normal dictionary. Yeah, I don't actually need default dict here. Default dict doesn't help. But that was just how I solved it before. Yeah, because we're not reading from it, so we don't care. Okay, so yeah, we can just use a normal mapping here. We're going to loop over each line in s.splitlines, and we need to do two things. We need to check if it's mask or not. So if line.starts with mask, then we're going to do our mask parsing. Otherwise, we're going to do our assignment. Let's actually do our assignment because I think that's going to be the easy part, or at least part of it. We're going to say match equals pattern.match line. We know it's not a mask, so it has to be one of these lines. So we're going to assert match is not none. Otherwise, we'll show the line if that assertion is not correct. And we're going to have two parts in here. We're going to have the target, which is going to be this integer here, and we're going to have the value, which is this integer here. So I did target value equals int match 1 and int match 2 to get those groups out. And then we're going to do bit logic here. Now, when we talked about this before, we know that we want to assign all the ones and assign all the zeros. That means we need to AND with zeros, and we need to OR with ones. So the way that I did this is I initialized mask OR and mask and I wanted to make these no-ops, so by default, in 2's complement, a OR with 0 is always just going to leave it the same, and a mask with AND is always going to, or an AND with -1, which is all ones, is going to leave it the same as well. Now, these initial values don't actually matter anywhere, but I think it's useful to put them there. But we need to actually parse the mask out of this, and so we need to parse this line. And I did, let's see, you do line.partition. I did a video on partition as well. And we want, let's see, we want the mask string. And what do we need to do? We need to get the ones out to OR them, and we need to get the zeros out to AND them. Okay, so then we can do, let's see, mask OR equals, also we're going to be using int thing, 2 to parse into base 2 in Python. So our OR mask, which is going to be our ones, so we're going to replace the x's, which we're ignoring, with zeros here because we don't want those to become set. So we're going to do mask s dot replace the x's with zeros. And we're actually going to do the same thing for ands, except we're going to replace the ands with ones. That way, the x's make no effect on the output. And yeah. So this will give us our two masks. And then finally, we're going to perform our actual assignment. So we do memory target equals value, but we need to OR it with this thing and AND it with this thing. So value OR mask OR and mask AND. And I think that should work. Oh, and then finally we need to, what was it, the sum of all memory. So we do return sum memory dot values. And I think that gets us our answer. It's gonna get a whole lot more complicated values in part 2 though. 51. What did I do wrong here? Hang on, I'm looking at my I'm looking at my solution. What did I do wrong here? Did I copy the example incorrectly? No, that looks right. Well, let's look at my actual solution. Day 14, part 1. Yeah, this looks exactly the same. This is exactly the same. I mean, I used default dict, but I don't think that changes anything. Target value. This is exactly the same. Oh, I grabbed the example wrong. This is the example for part 2. That's why. That would be why. Okay, we get the right value. I was like, I'm losing my mind. I'm pretty sure this is exactly what I did before. Okay, so that's part 1. Let's do part 2 now. Part 2 is a lot more complicated. Zeros are ignored. Ones set those bits. So that means we're going to be ORing with ones at the very least. And the x's cycle through all the values. So we're going to need to find the indices of all these x's and try every combination of those. So let's again have, well, we can copy some code from part 1. Like we can copy this regex. And we can copy most of this loop. We'll probably adjust it slightly. Okay. Part2.py description. Okay, so we still want to parse our mask similar to this. However, we don't have this. We have some different values here. So the way I chose to represent the mask was as kind of 2 parts. One to set the ones, and then the other to represent these cycled bits here. And these cycle bits, again, since we're doing one setting and 0 setting, we need kind of an AND mask and an OR mask. And so I basically had, the ones mask as an integer, and then I had the X masks, a bunch of them, which were a, list of tuple int, and inside those we had an AND mask and an OR mask. So that's how I built all those up. Now, unfortunately, my code is pretty complicated here, so I am going to paste some of it and kind of show you how I walked through it. I'm going to do kind of the most boring parts first, and then the more interesting parts after that. So this was the data structure that I used to keep track of things, was this mask name tuple. Now, note this has, the same structure that I was talking about here. We have a ones mask, which we're going to use to set all of these 1 bits. So that's this part here. Again, we're ignoring the zeros. They don't really come into play at all here. And then we have a series of X masks. And whenever we're trying to get targets, we want a bunch of different targets for one particular mask. And so we're going to loop through all of these X masks. And those X masks have ORs and ANDs. And we're going to take the number and OR the mask ORs and the mask ANDs. And so the way we're going to use this in our code is if we come down here, so we have to, to do implement mask parsing. And then if we come down here, we have our target and our value. So we're basically going to do for target in mask dot target, and we can pass in our target here. Target. Then we do memory target equals value. And again, we don't have to modify the value at all here. Now, the really tough part about this is the bit twiddling magic for computing all of these X masks, and I guess the ones mask as well, although that one's pretty straightforward. Admittedly, my code here is really gross, so I'm apologizing for this. Usually I would spend a little bit more time prepping this and trying to clean it up, but I honestly can't think of a way that's easier to explain than this. So, oh god, this code is awful. So I guess I'll talk about like how I went through this. So the ones mask is super easy. We just replace the x's with zeros, and we're going to be ORing this value later. So this just gets us the 1 bits out of here. So if we look at this here, we replace the x's with zeros, so we're just really assigning any of these ones here. That part's super easy. But then it gets tricky when we start talking about the x's. And the way that I thought about this problem is I wanted to get, let's say we have 0, x, 1, 0, or 0, 1, 0, x, 1, x, for example. So what I wanted to do here is I wanted to find the position of all of these x's. So in this case, these are the two positions, and I wanted to cycle through each of those bits. So what I thought about is, if we have two x's, we can kind of think of that as like a 2 binary digit binary number. And then we can just move each of those digits to the right positions and build up the ands and ors there. So that's what I kind of did here. So this range 1 left shifted by the length of x is going to give us a range. So like if we had, x's at 3, 4, and 5, 4 and 6, for example, that means there are two x's, and 1 left shifted by 2 is going to give us the value 4. And if we do a range from a range over that, we get the values 0, 1, 2, and 3. So these are all of the possible things, the possible combinations of bits that we have there. And again, we can do bin n. I guess let's actually do :b dot z fill 2. This will make it so it's filled to that many bits wide for n in this. We need an f. So you can see that it's all combinations of those bitwise numbers. So that's kind of what this loop is here. And then we have our number or and our number and again, these initial values should make sense to you. Like we're trying to build up all of the ones here, and we're trying to unbuild all of the zeros here. And so then we loop over every x in our list of x's, so these 4s and 6s. Now note these are the position from the left, not the position from the right. I probably could have made this make a little bit more sense instead of having to do this calculation twice by saying len s minus 1 minus this, and then we can just say xsj here, instead of having to do this weird bit shifting xsj, this weird extra math each time. So this probably simplifies it a little bit. But basically what this is supposed to represent is the position from the right-hand side now. And so if we shift by that number, we can move a bit to be right in that little position. And yeah, and so then we are looping over the index into the XS array. That way we can figure out which bit we need to AND with. So we're grabbing a bit out of each of these here. So that's shifting the bit over to match it and then shifting it back so it's just a boolean to an effect. I probably could have not done that second shift by just doing bool here. That way we get exactly a 1 or a 0, but I don't know. I felt that shifting it one way and then shifting it back was enough there. And then if this bit is a 1, that means we're going to add it to our ORs mask so that it's adding that 1. And if it's a 0, we're going to subtract it from our AND mask. That way it gets unset when we eventually AND it. And then, just append those. So this is kind of like how I parsed my bits there. This code is pretty complicated, and granted, I super did it on the fly, but, reproducing it right now, I'm not in the mental state to reproduce it at the moment. So sorry, you'll just have to deal with the copy paste here. But anyways, I use this parse mask function to build up a mask here. And so we can say mask equals parse mask s. Now we also want to initialize a dummy mask here just so our type checking is happy. Mark. Mask equals mask. And what do we have? We have an OR mask, so we want that to be 0. And we have a series of targets, and we can leave that series of targets empty. And so if we run this now, part2.py, name tuple is not defined right from typing import name tuple. We also need tuple. Anything else? We need generator. And we get 208, which is the answer that we expect down here. But anyway, that was my thought process here. Lots of messing with bits. I guess all of that hardware stuff that I've been doing recently has been paying off. But anyway, that's how I solved this problem. If we talk about algorithmic efficiency for both of these, the neat thing is this is just linear. We're really just looping over this list of lines, and we're not doing any complicated logic here. Now, this one's a little bit more complicated to talk about the algorithmic efficiency. This is very clearly a linear search here, but we do introduce some looping here in these parts here. But the amount of loops that could be possible in either of these cases is bound by the length of this string. And since this string length is constant, it's 36 bits, that means that this loop is a constant. So it doesn't actually factor into the overall runtime. The overall runtime is still just linear. But anyway, hopefully this is helpful. I'll see you again for the next day. Bye.